In this video, we're going to describe the implementation of convolution in digital domain. We assume that you are familiar with the concept of convolution and know its applications in signal processing, but have difficulties in implementing it in digital domain. Let's assume that the blue blocks are the signal and the red blocks are the impulse response, which is essentially another signal and usually shorter than our first signal. The process of convolution starts by moving the impulse response from negative infinity to positive infinity, one sample at a time, and multiplying each element of the impulse response with the corresponding element of the signal, and adding the result to get the corresponding element in our final result. As you can see here, before the first element of the impulse response reaches the first element of the signal, we don't have any output. Now that the first element of our impulse response is matched with the first element of our signal, we have 7 multiplied by 1. The signal is moved one sample, and now we have 7 multiplied by 2 and 8 multiplied by 1, which results in 8. If we continue this process, we reach a point that the last element of impulse response corresponds to the last element of the signal, and here you can see all the multiplication results. Now we have to add the intermediate values produced in each row, which are shown in the green colored blocks, to get the final value of each element in the result. The first value in the row is 7, and we proceed by adding 8 and 14 in the second row to get 22, and we repeat the process until all values of the elements of the output are calculated. It should be noted that the length of the convolved signal is equal to the length of the signal plus length of the impulse response minus 1. In real-time application, we cannot wait for the whole signal to be generated and then start to get processed. So the technique used is to wait for a block of signal with limited length to reproduce, and then start processing that block while the rest of the signal is being produced. As before, let's assume we have the same signal denoted by blue blocks and an impulse response denoted by red blocks. We consider the block size of 2 for this demonstration. So now we have 3 blocks which are named x1, x2, x3, and we have one leftover element. A simple way to deal with this element is to zero pad the signal, which means adding extra zeros to the signal to make it possible for it to become an additional block called x4. The impulse response is blocked in the same way, giving us blocks h1 and h2. Now if we convolve x1 with h1, we have the results shown with the purple block, which contains 3 elements. We continue by calculating the convolution of x1 by h2, then x2 by h1, and continue until all cross convolutions are computed. Overlap and add method, which was mentioned earlier, simply means that we have to put the result of the convolution of each of the 2 blocks in such a way that they overlap by a certain amount, and then add the elements which are on top of each other. Besides blocking, which helps to perform real-time convolution and increases efficiency for long signals, another improvement is to convert the signal and impulse response to frequency domain using fast Fourier transform. In this case, the convolution operation is simplified to element-wise multiplication of the 2 signals. We can then go back to time domain by using the inverse Fourier transform. This procedure is known as fast convolution. For any signal longer than 32 samples, this procedure is faster compared to time domain convolution. We hope you have more insight now into convolution in digital domain and the concept of fast convolution.